Hello, everybody. Welcome to another episode of the Day Zero podcast. Now, I will start off by mentioning this is a bit of a test episode. So, as some of you may know, before we went on our typical summer break, we had put out a few podcast episodes that were a little bit different from our usual coverage, which is just talking about vulnerabilities and exploits and breaking them down. And part of that was because topics were getting hard to find for a period there. Part of it was because we wanted to try changing the format to moving the vulnerability breakdowns and stuff to their own separate videos and keeping the podcast for more discussional type content. So we're doing a bit of a test episode for that here. So we're not going to be covering our summer experiences like we typically do on our first episodes back of the season, so to speak. But obviously it has been a little while since we put anything out. So how are you doing, Z?
Yeah, I mean, like I said, it's nice to be back. Nice to at least be trying to record something here, and we'll see how it goes. But yeah, I will give a quick shout out. I know we don't want to recap our summers, but I did update my whole getting started with exploit development post. Gave that a refresh, so it's out on our blog, or if you access the old one, link to that's there. Just as a quick shout out, that was something I actually got done during the summer, because as usual, we talk about streaming, we talk about doing things during the summer, and that just never happens.
Yeah, unfortunately. I really did plan to put stuff out, but it just didn't happen. So
Yeah,
that's how it goes.
That's kind of what I've come to expect is, have the big plans for that nice long break and, end up doing other things that take priority during that period. But like I said, it is nice to be back and actually recording something. We do have a couple discussions here to dive into. It is a change of format, so we'll see how this works. I appreciate any feedback over Discord or email or however you want to get in contact with us over, if you hate us for dropping the vulnerability summaries or something, you can direct that towards Spectre, but positive comments towards me. I'd appreciate that, but no, we appreciate any feedback.
I would not, but yeah.
Yeah, I mean, it really just comes down to any feedback on format and stuff would be welcome. We're trying something new here.
Yeah, and I will go into a little bit of the rationale there actually. For more of the background and whatnot, I would recommend checking out episode 253 of our podcast, which was a retrospective and future look into Day Zero. But it mainly comes down to the fact that while we do like doing the vulnerability breakdowns, and I know we have listeners that appreciate that, a lot of the times the format holds us back from going into the more technical vulnerabilities because it's really hard to break them down in an audio with an audio focus. Because obviously with the podcast, we try to make it as accessible to audio listeners as possible, so that you don't have to look at the video. We do have it as a screen share, so that it can help with trying to reference things, but we try to keep the audio only listening in mind. And it does hold us back from covering it. And I would like to do a more structured approach for covering vulnerabilities too. That way we can kind of bring things up and just have it more scripted in a sense. So that's kind of why we wanted to shift to doing more discussions. Obviously, we still do want to keep it technical. So we will still be going into the low level technical detail and stuff, but it's just it's going to be focused more on the discussion than the background information and everything that's involved. So that's a bit of the rationale of why we're trying out this different format.
Yeah.
So yeah, as Z said, we would appreciate feedback on it.
And with that, moving the vulnerability summaries out to their own content, hopefully it lets us, maybe explain things a little bit better. Pull in multiple vulnerabilities, perhaps, to explain a class or something. I don't know, it gives us a lot more options than just summarizing it.
Yeah.
That I think will ultimately help out. Or kind of help both, on our own end, just producing the content. Yeah, I don't know where I was going with that.
But yeah, I mean, we do have a few things to talk about in this episode. So one of them is a post that we came across on 4 exploits, 1 bug. So as the title implies, it's 4 different exploit implementations for a single vulnerability, which was in the WAPPD, which is the network daemon of MediaTek, and Realtek soft AP drivers. So yeah, this was kind of an interesting post, just based on like the methodology that goes into it. So Z, this was one that you really liked, and I'll let you take the lead on it.
Yeah, I kind of want to call this out. One, because this practice is something I think it's skipped over a little bit. People do it, but I don't see it mentioned a lot. That's just this idea of writing an exploit for the same bug multiple times. It's something that I end up calling out in our kind of post series from CTFs to real exploitation, or CTF to real world series, where kind of talk about getting good at exploit development and the process of going from once you have your basics, how do you actually start getting onto real world targets. And something I talked about is this idea of following a write up and then adding your own twist, or basically taking an existing exploit, maybe you followed the write up and then doing something else. And that's kind of what they went at here. In this case, they kind of had their approach of more building up to their final exploit targets. It's a little bit different, but this whole process is just something that I think when it comes to doing like end day development, especially, a lot of people focus on building the end day exploit and having just their exploit written up. And just following exactly, especially when you have a write up, following exactly what somebody else did, and all your troubleshooting is like, well, what they did didn't work, so like something's wrong, and figuring that out instead of trying to build their own path. And they call it out here as being focusing on the creative parts of exploit development. And that's kind of the important thing, or the important skill to build, especially once you know kind of your foundational concepts, like you understand a bit about ROP, you understand some of those core ideas. It's getting to play with these creative ideas and actually working those creative muscles a bit. So I appreciate this post on that front. And even if you don't do a lot of the binary things, we're probably going to talk kind of briefly about the exploit chains here, but or kind of the process they went through. But really, this is a process you could apply to any sort of bug, is just introducing your own constraints on exploitation so that you better understand how to exploit those issues, even if you're not actually in that situation, I guess, like creating situations you might fall into as a chance to play around with them. So good example of that I think would be dealing with cores. Even if like a bug you found, your environment doesn't have cores or you don't need to deal with it, introducing certain cores restrictions, depending on the bug, of course, like that is more of an excess thing, but dealing with those restrictions and trying to find primitives that'll work in that environment, I think is an important step in terms of how you're going to chain things together and such. And it's just the idea of introducing restrictions on yourself. So this case, they start off with your classic, just straightforward ROP chain. Is their first exploit is just they've got a stack based overflow. The initial bug is just they're on the stack. I believe during the second exploit here, they call out what their stack look like, but they have this KDP info sitting on the stack, and they can overwrite everything above it in the stack. And of course, their first exploit does the classic thing, which is just saved return address. This is a strategy that you basically learn first. Like every introduction to Stack Overflows has you do this. And they just kind of have the one mitigation on. Their second exploit, well, now they've turned on Stack Canaries, kind of the big one. So they can no longer take that same target, that saved return address. No longer do that. So they have to go to creating an arbitrary write by overriding one of the pointers that gets written to. And they control the data, so they're able to create the arbitrary write primitive, and they kind of build on, okay, they know this technique, now what else could they do here, what else could they corrupt? And also, as a side note, when it comes to stack exploitation, always something you should kind of look at. I think it's gain when you're learning, you kind of get that focus on the stack. You overwrite the saved return address, and sometimes that's your only option, sometimes that's not even an option. And sometimes, like in this case, you do have other things, like keeping in mind how far your corruptions can go, like where these things are allocated is another thing to kind of think about. Because sometimes what'll happen is you can actually go ahead and smash canaries because it's not going to return until, or maybe you're even in the buffer's allocated in a function that never returns. So like you can smash the canary to get access not to the return address, but to something else on the stack that's maybe passed down. That doesn't always happen. It kind of depends on a lot of things, but like there's a lot of options to kind of consider, and I think the important step is just look at what you can actually corrupt, not just what you know is your corruption target. And you would do the same process on the heap. You would look at what you can groom into place, what your options are for like an overflow. You wouldn't necessarily just jump onto I've got to corrupt the heap metadata, or at least not anymore. That was kind of the thing on Linux for some years with the unlink attack. But yeah, I kind of just want to call it this post is like this whole practice I think is really valuable. Third exploit, they introduced full, so I guess I should say second exploit, they get their arbitrary right and they write into the global offset table. Third exploit kind of kills that, and then last exploit, or sorry, third exploit kills that strategy for targeting, so they end up targeting a return address but kind of sniping it off the stack instead of overflowing it on the stack, so they don't corrupt the canary. Last exploit, they actually end up kind of dealing with the fact that in some situations you just don't have the primitives you need. They kind of, in a sense, accept defeat on their exploit only working towards termination because they couldn't corrupt the return addresses. And I don't know if we want to have any discussion about this, but I'm not sure how much they really explored for any sort of heap targets or any sort. I guess you would kind of want some sort of read though to get at that. But I don't know, Spectre, if when you went through this, did you have any thoughts on how they might have been able to get an exploit out of this? Obviously they know the target better, so any ideas we have probably just aren't valid for some reason that isn't explained. But I don't know, did you have anything?
Yeah. So when I was looking through it, I was kind of thinking that too. Like maybe there's some other pointer on the stack that could have been leveraged. But as you say, I didn't think about it too deeply because that high level thinking seemed a little bit too obvious for what they were trying to explore. So I didn't spend too much time thinking about it or like looking into the target to see if there would be some other way.
Yeah, on the stack, I don't know. A stack's always kind of rough. My thought was like, it didn't seem like they explored too much of the heap, but a big reason for that is they don't really have any read to get a heap address to know anything on the heap.
Yeah, like
And
the
without
thing
that,
is, yeah,
sorry.
it can be tough because with the stack, like it's basically as deterministic as you can get. Like maybe
Yeah.
the base address of the stack changes, but like the stack layout and everything is very deterministic. Whereas with the heap, even if you have like some pointer into the heap, like that doesn't necessarily mean you know where anything is.
No,
So
but
it's
you
a
can
lot
groom.
harder.
My
You
thinking
can,
is like,
but like your primitives are more limited. You have to have more control
mhm.
over the memory to be able to effectively take advantage of it. So, and without knowing all the intricacies of what they can do with what they have, it's hard to speculate on that.
Yeah, like I
But I
said,
did want to comment.
oh,
Sorry, go ahead.
I was just going to mention, like I said, it felt like they didn't explore it too much, although they kind of don't have the prerequisites to explore it. So maybe it's just totally fair that they don't have, because without having any reason to think that you'd be able to do anything on the heap, like get your right onto the heap, there's not much point in exploring it. Just usually, like it feels like any application is going to have a lot of things going on the heap. So that was kind of the missing thing I saw here, but they're also missing kind of the prereqs to be able to target that by only having a write primitive and not any sort of good read primitive. So yeah, go ahead.
But yeah, I did kind of want to comment on what you were initially talking about with like the reiteration part of it. And yeah, like the way I would put it is that it sort of forces you to explore your corruption logic and what you can do rather than just falling into those traps of going for what is common. Uh, so it's a great like strategy for when you're learning, I think. But it's cool too because it also gives you like the linear progression. Like you can kind of see as you're going through here, like you're adding more and more restrictions on yourself, and eventually getting yourself into a scenario that's close to, or basically is, the real world scenario. Because they start off with attacking this on x86, which with stack overflows, it's a little bit easier because, as he mentioned, you have that return address, which is the common target. Whereas on ARM, which is the actual architecture that you're going to be facing with like the Netgear things, they're generally going to be using reduced instruction sets. The return address is stored in a register. It's not stored on the stack. So Stack Overflow doesn't, like, you have to be a bit more creative with how you go about it. And like your whole ROP strategy is different too, because you have to account for that. But you don't start off with that right away, right? You start off on x86 where it's a bit easier and kind of progressively get to that point and see how far you can go. And I think that's a really smart way to approach trying to get more familiar with memory corruption logic. So
Yeah, and the other thing, not so much brought up in here, is at least in my mind, the idea of answering your own questions on would it be possible to exploit this given X, like given this mitigation being on, doing whatever, and kind of introducing things that way. One of the steps at least I learned a lot from when I was getting into the exploit dev was tackling questions. Basically, just like I'd have a question, why can't I do this, or why can't I do some other thing? Like in terms of a strategy, when I'd be reading a write up, why didn't they just do whatever thing? And then I'd go and kind of explore, oh, why didn't this work? Why wouldn't they have leaned towards doing that? And oftentimes I'd find like, oh, there's actually a reason, like it just doesn't work, or you know, if you might be reading this on like the stack aspect Spectre just mentioned, it's like, oh, the architectural differences mean that's less viable or something. And like kind of answering a lot of those questions, kind of like rabbit holing yourself in a sense. Like giving yourself those rabbit holes to go down is kind of just another approach on this I take. Obviously in this case they're building up, which I think is a great way to go about it. Start with the familiar, work towards your actual target, but also just tossing in those things that get the creative juices flowing, because exploitation, regardless of whether or not you're dealing with it as memory corruption or you're dealing with it on the web or whatever else, oftentimes does come down to your creative ability to think about how to leverage the primitives that you've got, be it a memory corruption primitive or just like a file write primitive or something. It's all just kind of these creative process to figure out what you can do, or at least as you get better, it is.
And what you were talking about with answering your own questions and rabbit holing yourself, it's a great way to build intuition up, because I think that's something that can be really tough when especially when you're first getting into memory corruption, is you look at write-ups from people who have been doing it for a while, and you have these questions of why they didn't do that. And the reason it's not answered in the write-up is often because it's just intuitive to the person writing it up. Like they're just like, yeah, I didn't explore that because I knew it wouldn't be worth exploring. But if you're getting into it, you wouldn't know why that's the case. And it can be kind of hard to build up that intuition just by like reading write-ups or whatever. But if you force yourself to try these things out and see why it doesn't work, it helps build that intuition, which over time will benefit you a lot, even other targets. It builds that hey, look at that. It builds that intuitive understanding. You just switch to the tab that has that sentence, and it helped me put into words what I was trying to say perfectly.
Yeah, I mean, it's like I said, the question answering, and just like if I have a question, taking the time, like especially when learning, when you have like all the time in the world in a sense. When I'm actually on like a professional engagement, I would not be able to just drop everything and go answer like a personal question. But when learning, I could. And like for me, I kind of mentioned as being like the most important tip, because it was a big thing for me, was just taking the time to dive into my own questions, and figuring that out and actually doing that legwork, because it is, we've talked about the rabbit holes before. Like going into rabbit holes is super important for just building up like a lot of random tidbits of knowledge that add up over time. So yeah,
Well,
it was.
So the other thing I'll say too is that we've been talking a lot about like for learning, but I think this kind of applies to even more experienced researchers too. Like even if you're just trying to grok on a new target, get up to speed on some new target, if this strategy is possible, it's a great way to get familiar with a new target as well. And the reason I say if it's possible is I think it is kind of important to mention that they are able to like compile and everything for this. There's source code. They can compile it with whatever mitigations they want. They can convert it between architectures pretty easily. If you're looking at like a closed source target, that is going to be trickier to do. Like applying constraints and removing constraints isn't as easy. Maybe it's still possible, but it might require more of the knowledge of the target to be able to do that in the first place.
Well, it depends on
but if it's possible to do, it is a good approach to take.
Yeah, like if you break away from the idea of constraints just as like the mitigations though, something I call it is just like, choose another target for your object. So
like imposing constraints on your own strategy for sure.
Yeah, that's kind of the route I'd go with dealing with a black box is I guess the own strategy constraints, not necessarily new mitigation or act like the mitigation is there, even if
pretending
it's not
like
CFI.
Yeah.
CFI would kind of be an obvious one that you can kind of fake in a sense. Even though it's not there, you can impose that restriction. That's kind of the approach I take on the black box. And yeah, in terms of getting up on like a new target, getting up to speed on a new target, I guess that kind of comes down to the difference between, like, say, a pen test and vulnerability research, where you have a lot of time to get on, like, you're getting up on target, you're learning a new target. Yeah, doing all the questions then, but when I'm on, like, a 5-day pen test or a 10-day pen test, you don't have the same amount of time to learn your target, but you also don't need to get as deep. So, like, that's kind of what I was thinking when I mentioned on a professional engagement. I'm maybe not going to dive into all the questions because you're a lot more constrained on the time. And getting that deep understanding of that specific target's less important. But yeah, no, you're completely right. Like, it is a good way when you've got that one target also, is it kind of forces you to explore and learn about the targets. So yeah, really good.
Yeah.
And I don't think I've seen any other write-up really actually doing this. I still just, maybe it's out there. I'm not going to say they're the first person to ever write this up. I either haven't seen it or haven't seen it in quite a long time. So it was kind of refreshing to see somebody taking this approach. And yeah, appreciate seeing the write-up on it.
For sure. So the other thing that was interesting that we wanted to talk about was talk on Twitter about an SGX breach. So SGX, for those not familiar, it's software guard extensions. It's an Intel thing. We've talked about it a few times on the podcast before. It is sort of like dead at this point. But it's basically Intel's method of providing like secure enclaves for doing attestation and isolating off memory from an untrusted operating system.
I guess you say dead, but it is still live in data center CPUs, but not, I think,
not in the consumer
lines. Yeah.
Yeah. So yeah, I mean, this kind of technology is important and it's been built up a lot because an untrusted operating system is something that is being factored into threat models more and more, especially when you're dealing with things like the common one is like DRM, which a lot of people like to jump on, but even just, securing private data from an untrusted OS, like that is a difficult problem to solve because for a long time an operating system has been considered the end all be all. It has control of the hardware. It can talk to everything. Like it's just it was considered all powerful for a long time. So in trying to change that, these technologies have been implemented where there's like IP blocks in the hardware, like in the chip, that even the operating system doesn't have unmitigated access to. And the way a lot of that security is guaranteed is through encryption and signing, relying on the mathematics there. And in order for the key material to be kept secret, it has to be stored somewhere that can't just easily be accessed, like the disk, like on disk storage or the flash memory or something. In a lot of cases, it's stored in internal fuses on the die. And for those that aren't familiar with what a fuse is, it's basically just, you can think of it as a link where if a bunch of current is driven through it and destroys the link, you have a 1, or otherwise, if it's an intact link and current can flow through it, it's a 0. And by having an array of these, you can encode data into it. Typically, you don't have a lot of these fuses on a chip. You'll have like a couple thousand or something, but you're not going to have like megabytes of storage or anything.
Yeah,
But
and
it's typical to store things like keys there because these fuses are really secured off from being able to be read or written to by blowing these fuses, and they're pretty hard to observe too, even if you get physical access to the CPU. They're really tiny on the die. They're really difficult to observe. So they're ideal for storing secrets. Sorry, go ahead there, Z.
I was just going to mention, you kind of ended up touching on it anyhow, but the difficulty of, like, once you've written it, generally speaking, you're not going to be able to change the value of a fuse. Like, if you've blown a fuse, you can't go back and, like, undo that process. Like they mentioned, it gets burned into the chip. So they're kind of dead. That can't easily be changed. And these fuse secrets, or fuse keys, end up kind of forming the root of trust for all the other keys they actually end up doing. And I pulled up a PDF here. It's like, I forget the title off the top of my head now, but it's like explaining SGX or SGX explained or something. And it's like this 118 page thing that kind of explains all the crypto and everything going on within SGX and how they do a lot of this. The key thing with this break, though, is that I guess we were talking about a little bit beforehand over what exactly was broken here. If it's um if they got both keys. So if you see in this PDF, or both, sorry, I'm going to do this. I'm going to use key and secret interchangeably. Technically, it's a secret that is in the fuses that is used to derive the key. And should also mention really quickly here, there's two secrets, two kind of fuse keys going on here. There's the sealing one. That is when, like, application, so in SGX, they could run like these secure applications, and it might have data that it wants to keep secure. It can seal that data. That ultimately ends up with a longer process using the sealing secret or the sealing key to seal data. And then there's a provisioning secret, which is used as part of Intel's kind of thing to say, yeah, I'm really, or as part of attestation, yeah, I'm really running inside of the secure enclave. I have access to these secrets. I'm really here. I'm really a true enclave. And Intel will actually keep I'm not sure if they keep a copy of the actual secret that gets put on for the provisioning key, or if they only keep a copy of the derivatives of it needed to verify. But basically, it's like a shared secret between Intel and the chip. So Intel can be like, yeah, this is really like our CPU. It really has access to this hard to read data, and like they can attest that this code's actually running like in their secure environment. And that, in theory, should give you some kind of confidence that, like, the code that you believe is running is really what's running, because they can attest to the fact that this environment is running this specific piece of code or this code block. And I believe Signal actually was using this to attest that their CPUs were actually running the code that they claimed to be running. So I don't know, Spectre, if you kind of want to take this back over. I kind of started explaining everything, but I think you have a better understanding over what exactly was leaked here and how. So maybe I'll pass this back over.
Yeah. So I don't want to go too much into like the attestation process, but the way that that works too is that the code that's running is hashed. So these are called like measurements. And those measurements are able to be verified because of the root of trust that's established ultimately from the keys that are derived from the fuses. So yeah, the whole idea here is that these fuse keys are supposed to be secret, and they're also supposed to be per CPU. I don't think we really mentioned that, but these are burned into each CPU from factory, and even if you compromise a key from one CPU, that doesn't imply that you're able to fake the attestation for another CPU directly. That is the whole idea of it. So if this fuse key or fuse key 0, as it's being called in this tweet, is leaked, it can be fairly significant for being able to bypass or fool the attestation. So it's something that has to be managed very carefully. So what happened in this case is the microcode in the Intel CPU that was managing these fuses failed to clear an internal buffer that had the fuse key 0 in it. which is a problem because you could then read or side channel that buffer in order to extract what the fuse key 0 contents are, which kind of breaks the chain of trust from the top down. Now, what makes this a little bit interesting and why we wanted to discuss it is Intel is kind of trying to downplay like the significance of this exploit, and then the researchers on Twitter are also kind of saying no, like this is a serious problem, and there are consequences that can be significant. So there's a little bit of interesting discussion there, and because it's dealing with like this fuse technology that isn't really documented that well, I think it's kind of interesting to talk about. So the first technical detail that is important that factors in between like Intel's response and the researcher is that this key material that's in fuses is actually encrypted. It's not like just plain text where you get it and then you have the key material to be able to drive all the keys. There is a layer of encryption applied there because this key that's in fuses is wrapped with the fuse encryption key, or the FAK. So Intel says there that like, hey, this thing you're getting isn't even usable as you're getting it. Like it's still encrypted. There's still some protection there. Sorry, I guess the tweet here calls it the global wrapping key. That's also kind of the problem when you have like these things that aren't documented too well and are proprietary, is that you have a lot of clashing terminology. So it can be a little difficult to follow. The problem there that's been pointed out by the researchers is that this global wrapping key is not unique per chip. It's the same across all chips of the same microarchitecture. So a determined attacker, which is well resourced, which when you're talking about these kinds of attacks is a fair assumption, I think. You're not having like random criminal gangs or something going after these keys. You're generally talking about well-funded actors like nation states and stuff. So the problem is there with it being shared across all processors is one could just get a processor that's on that same chip line. They could decap the chip or do whatever, whether it's glitching or decapping or whatever they want to do. And once they get that key, it's broken for all chips of that line, right? So they could still pull off this attack and end up decrypting the wrapped key into its plaintext form. It would require more effort to do it, but it would still be possible and feasible, given the threat modeling. Sorry, what were you going to say there, Z?
Yeah, I was going to mention that I'm not sure if it would only be nation states really doing this or capable of it. My mind immediately jumps when we're talking about the security stuff, into DRM, and of course that leads into piracy and the piracy groups.
That's true.
So I feel like that would be another place that would benefit from this, because as I mentioned here, getting the provisioning key, you're able to fake attestations. So with that, they could fake like, oh yeah, I'm totally running in this real Intel enclave, or in this real secure enclave, but I'm not. And then, the DRM goes ahead and sends any of its secret code over. Like that's something that I feel like the piracy groups would also be motivated to do and operate at a scale I feel like it wouldn't be too unreasonable. Granted, this is not an area I'm an expert in, so I know you've done a lot more of actually trying to like read information off hardware and stuff, and you know more about how practical some of that is than I do. But it feels like sort of,
you know what, that is actually a fair point. So I kind of ignored it, but it's true. Like when you're talking about mass piracy, like one example that comes to mind that I remember from like a training I attended about this stuff is like satellite TV and things like that. Getting the keys for that was very lucrative, to the point where it would make sense to spend like a couple $100,000 into the process of like decapping a chip. And that is like the neighborhood you're getting into when you're talking about trying to pull these keys from hardware by observation. Because you would need like high power microscopes, like scanning electron scopes and things like that, which range in the couple $100,000 to couple $1 million range. And then you would also need like specialty to be able to deprocess the chip and all that kind of stuff. So it is fairly expensive. That said, when you're talking about DRM on the level of like, I don't know, Netflix or something, that might very well make sense to factor in as like a reasonable capability for an attacker to have and expend the resources on doing that. So yeah, that's why these keys are like so important to be talked about here, and why I personally kind of agree with the researchers here in saying that just because the key is wrapped doesn't mean that being able to pull it isn't a problem, because that wrapping key, for all intents and purposes, can be considered compromise where it's shared across all the chips. It just depends on how much an attacker wants to put into getting that key. So yeah, the researchers are, I think, right here, and that it does have some serious consequences for SGX. The other kind of interesting thing about this, though, is the fact that Intel points out that you would need physical access to pull this off as well. So they say the external parties mentioned are running tests on systems that they have physical access to, which are not up to date with the latest mitigations and are not properly configured with Intel's flash descriptor write protection. And they managed to get into a state called red unlocked. So these findings are not surprising. So the red unlocked thing there is like the unlock state of the CPU, which allows them to like get access to this microcode and whatnot. And I mean, that is a fair thing to point out by Intel, because this doesn't seem like something you could just remotely do on some system. Like, let's say you RCE some system, you have code execution on it. I don't think you're really going to be able to pull these keys. You would still need physical access. That said, with the threat model that SGX has, don't think it's fair to like downplay it as if, oh, you need physical access, so it doesn't matter. I don't think that's really fair, because if you're doing this kind of protection to try to attest that secure code is running on the chip at early boot and everything, then physical access should be considered as valid for an attacker, I feel like, especially when you're talking about things like DRM, like Z was mentioning, where there might be some software that's trying to attest that these like the secure enclave and whatnot isn't compromised. So you have to consider a malicious user as part of the threat model there, I think, which is why I also never really liked that SGX also, I don't think Intel considered side channel and microarchitectural issues to be in scope either, or like as part of the threat model, which just seems weird to me, because it's like they're trying to pass it off that it provides protection from local attackers and everything without actually like guaranteeing that. I don't know. It's a little bit weird. So I did find Intel's response kind of interesting. It does have a little bit of merit, and I do understand like trying to push back and say like, hey, you do need this high level of access to pull this off. It's not an easy thing to do. But that said, you know, the researchers have a point too, that this should still be considered a serious problem.
Yeah, like we were kind of talking about this a bit beforehand too, where my thought is that local attackers and somebody doing this to themselves to extract the key is completely fair game, should be part of that threat model, and should basically be the baseline expectation for these sort of attacks. And if something were capable of being done remotely and like they could leak this somehow remotely, that would be an aggravating factor in a sense, rather than like the fact that it's not being a mitigating factor. If that makes sense. Like I would see it as, if this is remotely hittable, that raises the severity, rather than the baseline still kind of the physical attacker, because this level of attack is almost every time we talk about it, it's not something that can be done from a remote by a remote attacker. It's something that is being done physical. That is the main place, I think, where some of the threats exist. Because it is a self-attack, it kind of ends up meaning that you lose some of the trust. So I talked about how Signal was using it, I believe. I haven't looked into how exactly they're using it, so I apologize if my understanding's a little bit incorrect, but to kind of like verify that the code they publish is actually running on or within these enclaves, to kind of prove that like they've got open source code or whatever, like it's really running here, or at least the binary is really running. Again, I'm not exactly sure how this worked out, so I have an understanding that I'm working with that may be incorrect. And in that case, like ideally you would be able to say, okay, well, SGX is actually testing that this is the code that's running in there and like that's actually being used. And when the fact that those attestations can now be faked, you're back to just trusting a signal. Either Signal is just using SGX legitimately, um, or Signal is faking the attestation and like, it's actually all faked. You're back to just trusting Signal. You're back to step one. Even if Signal isn't doing it, you've kind of lost that trust because this vulnerability is possible. Um, of course, if they're running inside of like cloud environment and like it's not, I haven't actually looked. I don't think Google Cloud offers colo, but maybe they do. Co-location. Um, I haven't really looked into that at all. Maybe that would make a difference, but like if it's not servers they control, you can maybe have some trust there too. Like it's not a personally attacked server or something, but like generally just the fact the attack exists kind of violates some of the trust that you can have in SGX attestations at all. And unless they go and revoke the entire line of chips that you can do this on, uh, from being able to do the attestation.
Yeah, which
So
is something the researchers were kind of pushing for. But yeah, I mean, I doubt that's going to happen. Um, the other thing I wanted to bring up was that where this attack affects processors that are considered end of life, um, as pointed out in the original tweet that we have linked here, they are used in embedded systems. And that is kind of the other problem when you have these hardware level design issues, is that where it's at the hardware level and like if the fuse key is extracted and everything, there's just nothing that can really be done about it at that point without releasing like a new product and ensuring the new product is secure against the attack. Um, so, like, yeah, it might be valid at their end of life, but that doesn't mean that they're not still in use. So, that doesn't mean too much, in my opinion. The other thing that was mentioned by Intel was the fact that it relies on having, like, not being up to date with the latest mitigations. And I thought there was a bit of interesting discussion around this, too. Which is the fact that, hey, if you're just like trying to do this on yourself, or even if you're an actor that somehow has physical access to the machine you're trying to attack, then you'll just downgrade the system to a state where it doesn't have those mitigations and allows you to go through with the attack. Now there is some anti-downgrade protection that is available, but that doesn't necessarily mean that it's configured. And from some of the parties that are like more involved in this market and this kind of research, it doesn't seem like the anti-rollback is an on by default thing. It seems like something you have to enable. So, it's fair to point out that the fact that, hey, it does rely on these older mitigations, but that doesn't necessarily mean that, you're safe from the implications of the attack, because those kinds of downgrade attacks do exist. And when you're talking about a self attacker or somebody that has the physical access, it's hard to account for those kinds of situations. So, yeah, there was a lot of interesting discussion around this. Now, I will say this is fairly hard to follow. Before I got into this discussion, I went through and read like probably 30 or 40 pages of the white paper that Z mentioned earlier. This isn't an area that Z or I specialize in, so I am kind of taking some of the things that have been said by the researchers at face value, and the full technical details haven't been published either. So we kind of have to make some assumptions as well based on what Intel has said and what the researchers have said. But I still wanted to talk about it because it is kind of an interesting technology. It's something that is becoming more and more prescient in the space. And it's just a really difficult attack model to deal with. And seeing these kinds of vulnerabilities and the way that they're exploited is very cool. And yeah, I do think Intel is kind of downplaying a little bit here the severity of the impact. And that's not exactly anything new. That's kind of the commonplace thing for these companies to do, is to try to downplay a little bit some of the public view of what's going on, because it, like, to be fair, it does swing the other way too. There are people who saw this attack and are just like, oh, all Intel CPUs are broken. Or there's the more kind of insane thing where it's like, oh, this wasn't a vulnerability. This was by design. This was put there for the NSA and everything to be able to get access to your data. It's like, no, that's not what's going on here. But
Well, maybe. I have no idea. I am not in the place to be able to comment on that.
I mean,
although
part of that is it just drives me nuts because so I haven't seen it as much with Intel. I've been more focused on AMD, but with the AMD platform security processor, which I've put out some blog posts for on our blog, there is support for like a backdoor, for lack of a better word, like the secure unlock state that you can get into where you can run arbitrary code on the chip. But the thing is like, to enter that mode, not only do you need physical access, but the chip needs to be configured that way because there's things in fuses that prevent that mode from being accessed. You have to have the right keys to be able to even communicate with the relevant code and upload it to access the debugging backdoor. And I mean, what it's for is for debugging the chip. Like, that is a necessary part of the process. It's not like just anybody can easily get access into this mode. Even if you are like the NSA or something, it's still not easy. And when you're talking about these kinds of actors, like Big Brother and whatever, there's a lot of different ways they could go to get the data they want, and they probably don't need to go to that complexity of that complex of a level to do it. So I've always just kind of hated that that discussion aspect, and these people who were just like, oh yeah, this was an intentional backdoor and they just happened to find it. Like, no, that's just not how it works. But if you're where these things aren't documented and there's so much proprietary stuff around it, it's easy for that conspiracy kind of thing to come into play. So there is kind of the both extremes that are there. So I kind of understand why Intel would want to come in and like try to explain some of the nuances as well. So
yeah, it makes
that was
sense
just kind of being fair to Intel.
That Intel wants to, focus on how this is mitigated and the requirements of it. It just comes down to the fact that that's still part of the threat model. Like, in a lot of cases, like needing physical access is in fact a mitigating factor. That's going to be a pretty big deal. This, though, isn't one of those. This, has a potential impact. And like I was kind of mentioning, because this is all about trust, just the fact that it exists, even on older things, kind of violates some of the trust of the entire system. Like, it does have that sort of impact, which, it doesn't even matter. Just that fact. And in terms of understanding it, Spectre mentioned the PDF here, which super long, super in-depth, and very dense. I had also come across this SGX 101 Git book from SS Labs. So that's Georgia Institute of Technology. One of the few actual, I follow their publications, not so much for covering on the podcast, especially not anymore, but one of the few labs that is genuinely puts out some high quality research. So they've got this thing about SGX. If you are interested a bit more in how it works, how the enclaves work, it's not as detailed as the paper is, but it gives, I think, a more practical or more real world understanding. I found it fairly easy to kind of get through and kind of understand the high level, but yeah, the paper goes a lot deeper onto the fuses. This is talking more about how SGX on a whole as a system is working. So want to kind of shout that out as an option if you want to look into it, but the 100 and whatever page PDF is too intimidating.
Yeah. I mean, it's very interesting to look into and talk about, but getting the whole understanding of it is pretty difficult. So that said, if you are somebody who has more of that understanding and we have made a mistake in coverage or misspoken on something or whatever, do feel free to tell us that, because this is our sort of layman's understanding of it. I've read through some of the paper. I haven't gone through all 120 pages or whatever. But yeah, like it is a complicated area to understand, but that is also what makes it interesting. So
yeah, and I mean, with our discussion here, trying to focus more on like the impact and stuff, and less on here specifically how this vulnerability worked, which we didn't get into at all. So,
and part of
well,
that,
we
like I said,
barely
is
touched
because
on.
we don't fully know, because not all the technical details are public.
Yeah, that
Uh,
too.
so we have to infer and just trust on some of the statements. So that was the discussion on Intel SGX. That is most of what we wanted to discuss today. I know Z does have a shout out from Portswigger that he wants to cover, and then we'll wrap it up.
Yeah, just a quick shout out that it's kind of out there to take a look at if you're not already following everything coming out from Portswigger. They put out just a URL validation bypass sheet, and it's exactly kind of what you'd expect. It is a cheat sheet. I guess I linked the blog post announcing it, but the actual cheat sheet here, literally just examples of different URL bypasses, different. It depends on what's being checked, depends on your environment, but literally cheat sheet, different things for bypassing URL validation in whatever situation you're running into that. So things like you can toss to the fuzzer. I think they talk about this working with Intruder, or things that Intruder might already support. So yeah, just want to shout out that that's there to check out, to if you're testing, to get some inspiration from, or at least that's how I like to use cheat sheets, is as like if I'm testing something, oh, this is a good idea, I should take a look at how this is handled, and like kind of browse through and be inspired by that, rather than necessarily just this is how I'm always testing. But yeah, it's there. Figured I'd give it a quick shout out since it just came out a few days ago.
All right. So that was the episode, our little test episode here. As we said at the beginning, we would appreciate some feedback on the format change and what your thoughts are on it, as well as our thoughts to move the vulnerability summaries to dedicated videos that could be more structured. As I said, I know there are some people in our audience that really do appreciate the vulnerability breakdowns. So yeah, we just don't think it's great trying to keep it to an audio only context. So
And
yeah,
also, as a podcast, it also meant we were kind of covering the same sort of things a bunch, and then I'd have like some random little takeaway. Um,
yeah,
there's that aspect. I will say this particular episode, I do feel like we kind of leaned more into the binary side of things. Hopefully, there was still some value out of the discussion. Even if you're not doing the low level research. In the future, hopefully, some episodes won't only be like this low level, but this is kind of how our topics went this week. So
yeah.
if you are coming more from that website and you're like, this really doesn't work, I'd actually really appreciate feedback from those of you who are more on the bug bounty side over if there was any value out of this episode and how we can do that. Because something we don't want to keep doing is our split episode of Bounty Binary, and being able to do just a single episode in a week to cut down on kind of some of the time we're actually spending on this too.
Yeah. And what the balance is going to be between the low level and web is largely going to depend on like the week and what discussions we have lined up. So that is something that's not going to be a fixed constant. It's going to change. So yeah, it's something we'd appreciate on how we should strike that balance. That would be good to get some feedback on. But yeah, I think that's pretty much everything that we have to say for this episode. Thanks for tuning in, and we'll see you on the next one.